Welcome back to the deep dive. If you're like us, you're constantly trying to make sense of new research, maybe for work, maybe just, staying informed.
Oh, yeah. And the sheer amount of information out there, it's just overwhelming sometimes.
It really is. How do you find the solid evidence, the stuff you can trust?
How do you cut through all that noise and get a clear picture? That's the challenge.
Exactly. Which is why for this deep dive, we're tackling something really fundamental for evidence-based practice: systematic reviews and meta-analyses.
Right. Think of them as tools, basically. Really powerful tools designed to do just that, sort through the evidence.
We've pulled together a bunch of sources, library guides, academic articles, some blog posts too, to help us unpack what these are all about.
Yeah, got a good mix here.
So our mission today is to kind of cut through the jargon, show you how these reviews work, why they're seen as so important, and critically, how you can approach reading them and actually use what they find.
Getting to the core insights, basically. The stuff you need to know.
Let's start right there then. What actually makes a systematic review? Well, systematic.
Good question. The sources really stress this. It's not just, any old literature review. A systematic review synthesizes evidence on a clear topic, but it uses critical, transparent methods and crucially reproducible methods.
Reproducible, okay.
Yeah, to identify, define, assess, and then summarize the research.
And that word systematic is the absolute key, isn't it?
It's everything. The methods, how you find studies, how you select them, how you appraise their quality, they're all decided on and spelled out before you even start searching.
Ah, so it's planned up front.
Totally. It's a deliberate process. The whole point is to minimize bias, stop researchers, even unintentionally, from just cherry-picking studies that back up what they already think.
Okay, so that's the big difference compared to, say, a traditional literature review, like a narrative review.
Exactly. A narrative review gives you a good overview, it evaluates stuff, sure, but the methods for finding the studies, they're usually not specified up front in that same rigorous, transparent way.
Right. The search might feel comprehensive, but it's not necessarily exhaustive in that same systematic sense.
Precisely. Narrative reviews are great for background, for getting the lay of the land, but systematic reviews, because of that explicit, planned-out method, they're generally seen as the highest level of evidence.
Especially in fields like medicine or public health, where decisions really matter.
Yeah. They're specifically designed to cut down on bias, where those traditional reviews might be more, vulnerable.
Okay, that makes sense. Now, what about meta-analyses? You always hear them mentioned together with systematic reviews. What's the relationship there?
Yeah, they're very close cousins, often done together, but they are distinct things.
Okay.
So the systematic review is the whole process, the searching, the selecting, the quality checking of the studies. That's the detective work.
Finding all the puzzle pieces, like you said.
Exactly. The meta-analysis, on the other hand, is a statistical technique. It takes the numbers, the quantitative results from the suitable studies found in the systematic review.
Suitable meaning similar enough.
Right, similar enough to combine, and it statistically merges them to create a single pooled result, like an overall effect size for the intervention or exposure.
So meta-analysis is the kind of number-crunching part that happens after the systematic review has gathered and vetted the data.
Spot on. But, importantly, you can have a systematic review without a meta-analysis. If the studies are too different to combine statistically, you just present the findings systematically.
But you can't do it the other way around.
Nope. You can't just do a meta-analysis without doing the systematic review work first to find and vet the studies properly. The systematic review is the foundation.
Got it. The meta-analysis is like the statistical summary built on top, but only if the building blocks actually fit together. So why are these methods considered so valuable? Why go through all that rigor?
Well, the big thing is they aim to give the clearest possible summary of all the current research on a specific question, reducing the chance you get misled by maybe one quirky study result or, a researcher's personal bias.
And they help overcome the limits of individual studies too, right? Like one study might be too small to really show an effect.
Absolutely. By combining data, a meta-analysis basically creates a much larger sample size that gives it more statistical power.
Power to detect effects that smaller studies might miss.
Exactly. And you get a more precise, more reliable estimate of the true effect. They help make sense of sometimes conflicting findings across different studies and pull out the best quality data from that, huge sea of information.
It's like getting a weighted average of the best evidence, which is obviously super valuable for making informed decisions in healthcare, policy, lots of areas. It lets you start at the top with the strongest evidence.
Right. So given how important they are for guiding decisions, how do researchers actually do one? Let's get into the actual
Okay,
process.
yeah. The sources map out several key stages, and it always starts with the research question.
Has to be sharp,
Right.
clear, answerable.
Precision is key here, you mean?
Totally. For quantitative questions, things like clinical trials, they often use frameworks like PICO, that's population, intervention, comparison, outcome, help structure the question really clearly.
And for qualitative research?
PICO is common there, population, interest, context.
I also saw spider mentioned in the sources. That looked interesting.
Yeah, SPIDER's another good one, especially highlighted for qualitative synthesis. It stands for sample, phenomenon of interest, design, evaluation, and research type.
Can you give me an example?
Sure, the sources had one. What are young parents' experiences of attending antenatal education? So S is young parents, P of I is the antenatal education, D is the study design like interviews, E is evaluation their experiences, and R is research type qualitative. It forces you to break it down.
Okay, that helps pin it down. So once the question is really nailed down, what's next?
Then you define your inclusion and exclusion criteria. These are the rules. Which studies get in, which stay out. Things like study design, participant characteristics, maybe language, publication dates. You have to be really explicit about this because it shapes the entire evidence base you're building.
And the sources mentioned something about handling different patient numbers.
Yeah, you need a plan for that. If a study reports slightly different numbers at different points, you need clear rules on which number you're using for your analysis and why. Transparency again.
Right. So clear question, clear rules, then comes the big search.
And this is where that systematic part really shines. The goal is a broad, comprehensive search. You want to find all the potentially relevant studies that meet your criteria. Missing studies is a major source of potential bias.
So where do you look? Not just PubMed, I assume.
Definitely not just PubMed or Medline. You start with the big databases, sure, Medline, Embase, Cochrane Central. But a rigorous search, as the sources emphasize, goes way beyond that.
Like where?
You need to look for gray literature.
Gray literature, what's that?
Things like conference abstracts, technical reports, theses, stuff that isn't published in the usual journals. You also search trial registries for ongoing studies, contact experts in the field, and check the reference lists of the papers you do find.
That reference list checking. They called it pearl growing.
Yeah, I like that term too. You find one relevant pearl of a study, and its references might lead you to others. You also do citation searching, see who cited the key papers you found.
Sounds incredibly thorough.
It is, and complex. That's why the sources strongly recommend involving an expert, like a research librarian or information specialist, to help design and run these searches properly, make sure they're reproducible.
Okay, so you've done this monster search. You have maybe thousands of titles. How do you whittle that down?
That's the study selection stage. First, you screen the titles and abstracts. Then, for anything that looks promising, you get the full paper.
And who does the screening?
Crucially, this should be done by at least 2 reviewers working independently to minimize bias. One person might misinterpret criteria or miss something. Having 2 independent checks adds objectivity.
What if they disagree on whether to include a study?
They discuss it, try to reach a consensus based on the predefined criteria. If they still can't agree, a 3rd reviewer often acts as a tiebreaker.
And you have to document all this.
Absolutely. You need a clear record of the flow of studies, how many you started with, how many were excluded at each stage, and why. Again, for transparency and reproducibility.
Right, that word again. Okay, study selected. Next.
Data extraction. Now you pull out the relevant information from each included study according to your plan. Details about the participants, the interventions used, the outcomes measured, the results.
And again, 2 people doing this independently.
Yes, ideally. 2 reviewers extract the data, then they compare notes, resolve any discrepancies. It helps catch errors.
Makes sense. What if the studies report data differently, like different units or something?
That's a key point the sources raise. If data formats or the units used, or maybe the time points when outcomes were measured are too different across studies, it might actually limit your ability to combine them statistically later in a meta-analysis.
Ah, okay. You need apples-to-apples data as much as possible. Get about the quality of the studies you've included.
Absolutely critical stage. Assessing the risk of bias, Rob, or the methodological quality.
Even for studies like randomized controlled trials, which are supposed to be high quality.
Especially for RCTs. Just because it's called an RCT doesn't mean it was done perfectly. The sources are really clear on this. You must evaluate the internal validity. Because if the studies you include are flawed, your overall result, especially from a meta-analysis, could be unreliable. Low quality in, low quality out.
So how do you assess that risk of bias?
There are standard tools. The Cochrane Risk of Bias tool for RCTs is very common. It looks at specific areas where bias might sneak in.
Like what?
Things like, how were participants randomly assigned? Was that assignment process hidden, concealed? Were the participants and researchers blinded to who got which treatment? Was data missing, and how was that handled? Were all the planned outcomes actually reported? And other potential biases, too.
So it's digging into the details of how the study was conducted, not just accepting the label.
Precisely. Critical appraisal isn't just describing the methods. It's judging how likely the results are to be trustworthy. It's how you get beyond just, counting studies on each side, that old vote counting idea, which is totally discredited now.
Right. You want to weight things by how robust the evidence is, like the grade approach does.
Exactly. GRADE uses these appraisals to rate the overall certainty of the evidence for making recommendations.
But the sources mentioned a really important, maybe concerning point about how this ROB assessment is actually used, or sometimes isn't.
Yes, this is a huge takeaway. It's a major challenge highlighted in the sources. Often, even when reviewers do carefully assess the risk of bias in each study, that assessment doesn't get fully factored into the final synthesis or the conclusions, especially in reviews looking at non-randomized studies.
Wait, so they identify potential flaws, but those flaws don't really change how much weight that study carries in the end result.
That's the danger. It kind of undermines the whole point of assessing bias in the first place, which is to make sure your conclusions are based on the most trustworthy evidence, not just an average of everything, flaws and all.
Wow.
The sources really stress there's a need for reviewers to be much clearer about how the critical appraisal influenced the synthesis. Just calculating a summary Rubley score, which used to be common, isn't enough. You need to see how specific biases might affect the results.
That's a massive point for anyone reading these. You need to check if they assessed bias, and then how that assessment actually shaped the final conclusion they draw.
Fundamentally, it affects how much trust you can put in what they're saying. Okay, so you've done selection, extraction, quality assessment. Now you analyze and synthesize. And this is where you might hit that fork in the road we mentioned earlier.
Right, if the studies are too different.
You do a qualitative synthesis. You describe the findings from each study, maybe group them, look for patterns, but you don't crunch the numbers together statistically, often presented in tables, with a narrative summary.
But if the data are similar enough...
Then you perform a meta-analysis, a quantitative review.
Okay, let's dive into that analysis part, the meta-analysis. The goal is more power, more precision.
Exactly. By statistically pooling results, you get that bigger sample size, a tighter estimate of the overall effect, and a better chance of detecting a real effect if it exists.
And the main way we see this presented is the forest plot.
That's the one. The forest plot is standard. For each study in the analysis, you'll see a symbol, usually a square. Its position shows the study's result, maybe an odds ratio, maybe a mean difference.
And the size of the square means something.
Yep. The size represents the study's weight in the meta-analysis. Bigger squares mean more weight, often because the study was larger or its result was more precise.
And those horizontal lines coming up from the squares.
Those are the confidence intervals, the CIs, for each individual study. They show the range where the true effect for that study likely lies. Shorter lines mean more certainty or precision.
Okay, and then the overall result.
That's usually shown at the bottom as a diamond. The center of the diamond is the pooled point. Estimate the overall effect from combining all the studies. And the width of the diamond represents the confidence interval for that pooled result.
Got it. And there's always that vertical line.
Right, the line of no effect. It's typically at 1 for ratio measures like odds ratios or risk ratios, or at 0 for difference measures like mean difference.
And if the diamond crosses that line?
If the diamond's confidence interval overlaps with that line of no effect, the overall pooled result is usually considered not statistically significant at the conventional level, like P0.05.
That visual is really helpful for seeing it all at once.
Yeah.
You mentioned ratio versus difference measures. Can you quickly recap those?
Sure. It depends on the outcome type. For dichotomous outcomes, things that are yes, no, happen, didn't happen, you'll see things like odds ratios or XR, risk ratios, RR, or maybe risk differences, RD.
And an OR or RR of 1 means no difference.
Correct. Values above or below 1 tell you the direction of the effect. Sources also mention an NT number needed to treat. It's a way to interpret the risk difference, basically telling you how many people need the treatment for one extra person to benefit. Very practical.
Yeah, NNT feels more intuitive sometimes. And for continuous outcomes,
Yeah.
like blood pressure or test scores.
There you use mean difference, MD, if all the studies measured the outcome on the exact same scale. Or if they use different scales measuring a similar underlying concept, you use standardized mean difference, SMD.
And for MD and SMD, 0 is the point of no difference.
Exactly. Positive or negative values show the direction of the effect.
Okay. Now, a big choice reviewers make is the pooling model. Fixed effect versus random effects. Why does this matter so much?
It really does matter. The fixed effect model basically assumes there's only one true underlying effect size across all the studies, and any variation we see is just random chance or error.
So it assumes the studies are really similar.
Pretty much. And because of that assumption, it tends to give much more weight to the larger studies in the analysis. Methods used include inverse variance, Mantel-Haenszel, Pareto.
And the random effects model.
That one makes a different assumption. It assumes the true effect size might actually vary from study to study, maybe because of differences in the populations or how the intervention was applied or the setting.
So it allows for real differences between studies plus random error.
Exactly. It accounts for that between study heterogeneity. As a result, it gives more balanced weight across studies. The smaller studies get a bit more influence compared to fixed effect, and the largest ones don't dominate quite as much.
When would you use random effects?
It's generally preferred when the studies seem different, or when you actually detect statistical heterogeneity. Common methods are Dursimonian and layered, or inverse variance for continuous data. And the sources mention Hutton-Knapp-Sittig-Junkman, which is apparently better when you have only a few studies, like fewer than 10.
So the choice really hinges on how similar you think the studies truly are.
Yeah. And critically, the sources point out that using the same data but applying a different model, fixed versus random, can sometimes lead to different overall results, maybe even change whether it looks statistically significant or not.
Wow. So how do researchers check that?
Sensitivity analysis is key. Rerun the analysis using the other model, or maybe leave out certain studies just to see how robust the main finding is to those analytical choices.
Okay, that brings us neatly to heterogeneity, that variability between study results you mentioned. How do you actually measure that?
Well, you can look at the forest plot visually. Do the results seem all over the place? Do the confidence intervals overlap much? But there are formal statistical tests, too. Cochrane's Q-test is common. It gives you a chi-squared statistic. Traditionally, a p-value less than 0.1 for this test is taken as suggesting statistically significant heterogeneity.
And I remember seeing IRA mentioned a lot.
Yeah, iron-80 is probably used more often now. It quantifies the percentage of the total variation across studies that's due to genuine heterogeneity rather than just chance.
What do the percentages mean?
Generally, 0 to 25% is seen as low heterogeneity, maybe up to 50% is moderate, and anything over 75% is considered high heterogeneity.
And if you find high heterogeneity, what do? Use the random effects model.
That's one approach. Or you might decide not to pool the data at all if it's extremely high. Or you could try to explore why the results differ using subgroup analysis. Maybe the effect is different in older versus younger patients. Or meta-regression, which tries to relate the effect size to study characteristics.
So heterogeneity isn't just noise. It can actually tell you something interesting about how the effect works in different situations.
Exactly. It might be a signal, not just random variation.
Okay, another big potential problem. Publication bias.
Ah, yes, a major headache. Publication bias is this tendency for studies with statistically significant positive findings to be more likely to get published than studies with null or negative results.
Which means the published literature isn't the full picture.
Precisely. If studies finding no effect, or even a harmful effect, just sit in file drawers and never get published, then a meta-analysis based only on the published stuff could give you an overly optimistic, biased estimate of the true effect.
How can you even detect that? How do you know what's missing?
You can't know for sure, but there are tools to look for suggestive patterns. The main one is the funnel plot.
How does that work?
It's a scatter plot. It plots each study's effect size on one axis against some measure of its precision or size on the other axis. If there's no publication bias, you'd expect the plot to look roughly like a symmetric, inverted funnel study scattered fairly evenly on both sides of the overall effect.
And if it's skewed?
If the funnel looks asymmetric, maybe with a chunk missing on one side, often the side representing smaller studies with non-significant results, that's a warning sign for potential publication bias.
Are there stats tests for that asymmetry too?
Yep. Tests like Begg's test or Egger's test can statistically assess the funnel plot asymmetry. And there are even methods like trim and fill that try to estimate what the overall effect might look like if the supposedly missing studies were included, though those methods have their own assumptions.
Okay. And finally, on interpretation. You mentioned p-values earlier. What are the common traps?
This is so important. In a meta-analysis output, you usually get a p-value for the overall effect, maybe from a z-test, and also that p-value for the heterogeneity test, the chi-squared.
Right.
A really common mistake is seeing a p-value greater than 0.05 for the main effect and concluding there is no difference or the treatment doesn't work.
When really
It means we didn't find strong evidence of a difference. Or the data are compatible with no effect, but also potentially with a small effect. You always need to look at the confidence interval. Does it include clinically meaningful effects? Does it exclude them?
Because absence of evidence isn't evidence of absence, basically, especially if the overall analysis still lacked power.
Exactly. And another thing the sources highlight, in really huge meta-analyses with tons of participants, even a tiny clinically insignificant effect size can end up with a very small p-value just because of the sheer sample size.
So the p-value alone can be misleading.
Totally. You have to look at the magnitude of the effect, the actual OR or MD value and its confidence interval, and judge if that size of effect is actually meaningful in the real world, not just statistically significant.
Okay. So we've covered the standard review, focused on intervention effectiveness pretty thoroughly. But the sources mentioned there are actually lots of other types of systematic reviews, too.
Oh yeah, the methodology has been adapted for all sorts of questions. There are reviews specifically for diagnostic test accuracy, how good is a test at spotting a disease. There are reviews looking at methodology itself.
And qualitative reviews?
Yep, qualitative systematic reviews that synthesize findings from qualitative studies, maybe using methods like meta-ethnography. There are reviews of prognosis, what's the likely course of a disease. Overviews or umbrella reviews, these actually synthesize the results from multiple existing systematic reviews on a topic.
Wow, reviews of reviews.
Yeah. And living reviews, which are cool, they're designed to be continuously updated as new relevant studies come out. Very useful in fast-moving fields. And rapid reviews.
Those sound useful for quick decisions.
Exactly. They still use systematic methods, but might streamline or skip certain steps to get an answer faster, maybe for urgent policy questions. They trade off some rigor for speed.
And one other type was mentioned, specifically scoping reviews. How do they fit in?
Scoping reviews are a bit different. Their main goal is usually broader. To map out the existing literature on a topic, see what's out there, how much research exists, what kinds of studies, identify gaps in the research.
So less about answering a specific narrow question.
Right, more about understanding the landscape. They help determine if a full, focused, systematic review is even feasible or needed. They use systematic search methods, but often the quality appraisal step is less rigorous or might be skipped compared to a standard systematic review.
Okay, so all family of review types. Now, thinking about all these systematic methods, they sound incredibly powerful, aiming for that gold standard. But what are the catches? The limitations or challenges we need to keep in mind?
Well, despite their strengths, they're not perfect. One big issue is they can become outdated fairly quickly, especially if the field is moving fast. New major trials might come out right after a review is published.
And just because it's called a systematic review doesn't mean it's a good one. Right.
Absolutely not. The quality varies enormously. Some are done really well, others not so much.
And bias can still creep in.
Oh, definitely. We talked about publication bias. But also, if the search wasn't truly comprehensive, maybe they missed key gray literature or studies in other languages, the result can be biased.
What about the methods themselves?
Sometimes reviewers might, maybe subconsciously, change their methods or inclusion criteria after they see the results, which can introduce bias. Publishing a protocol up front before starting is really important to help prevent that.
Yeah, reporting issues.
Huge problem. Poor reporting and not following guidelines like PRISMA makes it really hard for you as a reader to judge the quality or even understand exactly what they did. Data extraction errors can happen, though having two reviewers helps. Search strategies might not be described well enough for someone else to replicate them. Eligibility criteria might seem arbitrary.
And that point you made earlier about integrating the bias assessment.
Yes, worth repeating because the sources really emphasized it. That critical flaw where the risk of bias is assessed, maybe meticulously, but then it doesn't seem to actually influence the synthesis or the final conclusions nearly enough. Especially common, apparently, in reviews of non-randomized studies.
So the conclusion might still lean heavily on flawed studies, even if the flaws were noted somewhere in the text.
That's the risk. It disconnects the appraisal from the synthesis.
Hmm.
As a reader, you have to actively look for how or if they incorporated those quality judgments into their final take. It's not always obvious.
That's a really critical point for users of these reviews. Okay, let's try and wrap this up. What's the main takeaway from this deep dive into systematic reviews and meta-analyses?
I think the main message is that when done well, these methods are genuinely powerful. They are designed to be the most reliable way we have to synthesize research findings, to filter out noise and bias, and give us a solid foundation for evidence-based decisions.
They aim for that objectivity and thoroughness that, a quick traditional review just can't offer.
Right. And it's a big but. You absolutely cannot accept their findings uncritically.
You need to look under the hood.
Exactly. You need to understand the process. How clear was the question? How comprehensive was the search? How were studies selected? How was quality assessed? And crucially, how did that quality assessment actually shape the final synthesis and conclusions? How did they handle differences between studies, that heterogeneity? Did they look for publication bias?
It's not enough to just read the abstract or the final sentence.
That's not at all. You have to engage with the methods. The strength of their conclusion is directly tied to the rigor and the transparency of the steps they took to get there.
This has been fascinating. We've really seen both the incredible potential of these tools, but also the nuances and the potential pitfalls.
They are rigorous methods, definitely. But being a savvy, critical reader, someone who understands the process, the potential limitations, and especially asks, how do they factor in study quality? That's what allows you to use these amazing resources wisely.
Which leaves us with the final thought for you, our listener, to think about. Considering everything we've discussed, especially that point about how even in well-done reviews, the assessment of study quality or risk of bias doesn't always seem to fully impact the final conclusions. How might you change your approach the next time you read a systematic review?
Yeah, what specific things will you look for beyond just the headline result or the p-value? How will you gauge the true strength of the evidence presented?
Something to mull over. Thanks so much for joining us for this deep dive.